Hi, and welcome to the Practical Engineering Solutions channel. My name is Jack. Today we're going to talk about a gadget I've been using for a few years now, and I really make a lot of use out of it. It's a lightning detector. I want to make clear at the beginning that I did not design the circuit for this lightning detector. It was online. There's a whole ton of different circuits online. This is one I chose, and it worked pretty well, and I've made some modifications in addition to it. So I'll put the link down in the description for the site that has several lightning detector circuits on it, and also it also gives you an idea of what people have done to package them. Okay, let's take a look. Okay, let's talk about a lightning detector. So what are some of the uses for a lightning detector? Well, obviously warning of approaching storms, depending on the type of detector you build, and the antenna can measure storm activity from 50 to 200 miles away. Also, it gives you an indication of how severe the storm is, or could be. It's also good for alerting amateur radio operators, like myself, to ground their antennas. And also, they can be made portable. They're easily made portable, so if you're out in the open, it can give you a warning to take cover, especially if you're on the water. And they're easy to test. There are simple circuits you can make to test the lightning detector, or in my case, I use a switch next to it that turns on a fluorescent light, and if I do that 4 or 5 times, it simulates lightning. Okay, so what does the basic circuit look like? As I mentioned before, this circuit was on the web. It was developed by an individual named Charlie Wenzel, and there are many circuits on the web. And as I mentioned, I'll put the link in the notes here. But basically, this circuit here that I built is a radio, and it measures, or it looks at 300 kilohertz. These two inductors in this capacitor form a tank circuit, or a tuned circuit of around 300 kilohertz. Why 300? Well, because it's where a lot of the lightning activity occurs. It's below the AM broadcast band, so you want something that is not going to trigger based on radio signals from the AM broadcast band, and it's wideband enough so it'll pick up any kind of lightning strikes. The second part here of the circuit is an amplifier, right where I'm showing here. And then these two transistors here are what's called a flasher circuit. So it strengthens the pulses and lengthens the pulses for the rest of the circuitry. There are two outputs here which I'm going to show where they connect, part A and part B. The pulse output is here. It's negative going pulses. And the power supply is a 5-volt battery or wall watt. I happen to use a wall watt because I keep this in the lab down in the basement, but you could easily run it off of a battery. Okay, the first accessory we're going to do or talk about is a speaker output. And this connects to A in the previous circuit, and it produces a speaker output. Now what you hear here is a very quiet noise. It's kind of like hot water on a skillet. It's fairly quiet. So if you want something that's loud, you probably want to put an amplifier on the other end of this. Also, my speaker is not a 16 or 39 ohm speaker. I think it's an 8 ohm speaker, so that could have something to do with it too. It's pretty quiet, but it's loud enough that you can hear it and you know it when it's on. And I would put a switch on it, because if you don't, you're going to regret you didn't put a switch to turn it off, especially in a loud thunderstorm. The next output is an LED output. So you have a flashing LED every time a lightning strike or pulse hits this, and you connect that to the pulse output, which is part B, or point B. Okay, the next accessory is a meter circuit, naturally. We want to be able to measure and see on a meter how severe the lightning is, or how many counts or pulses there are coming off the lightning detector. So this connects to the pulse output on the basic circuit. And this is a 100 microamp meter. And then it connects to point C. It has a 0 to 100 millivolt DC output. This is the meter circuit, and it has a capacitor here for a little bit of smoothing of the pulses. Okay, next thing I built, which I added and developed, is this buffer and interface circuit. I have a home automation system, and 100 millivolts just isn't going to do it for it, which is the output of the meter circuit. So I took the output of the meter circuit, which is point C, and I made this simple circuit with a gain of around 50 to convert the 100 millivolts coming in to 0 to 5 volts, because that's what my home automation system requires in its analog input. So you can see here an output of my home automation system. This is a screenshot, and you see here it says lightning equals 1%. So as the lightning gets more and more intense, that will go up to 100%. Now, how did I do that? Well, the actual voltage coming out of that buffer circuit is 0 to 5 volts. The analog value that that is seen by the home automation controller, it converts those voltages into a score of 0 to 255. And then in the software of the home automation system, I have it multiply this analog value by 0.39 so that the percentage goes from 0 to 100 instead of 0 to 255. So that's how I get 0 to 100. So that lines up with the meter that's 0 to 100 microamps. Now the power supply and on-off switch, this is pretty straightforward. I use a 12-volt wall wart, and when the power is on here, it goes to a LM309 to give me 5 volts out. It also goes to this little divider circuit to give me 6.75 volts, and that goes to the buffer circuit I showed you before that changes the output from 100 millivolts to 0 to 5 volts. That requires a 6.75 volt supply. The other side of the power switch, one way it's connected to the antenna. That's this way here. This way the antenna is connected to ground. So when the power switch is off, the antenna is grounded. When the switch is this way, there is no connection to the antenna, and the antenna goes right into the input of the lightning detector. So this switch grounds the antenna when it's turned off, as well as turning the power off. Okay, this is the package I put it in myself. This is just like a bud box, and it's got some kind of veneer on it, contact paper I should say. This is the power switch, turns it on and off, the speaker that I showed you, and this is the LED trigger, and then this is the meter. This is a top view inside the box. This is the LM309 regulator, the 5-volt regulator. These are the coils at the front end, and the transistors are in here. This is the meter, obviously, and the switches. And then I'll show you the back panel. This is with the speaker attached. All I did was I put a right angle bracket here and attached the speaker. And in the back, you see here there is a antenna on the right. This is the ground. I connect that to a water pipe. My antenna is about, it'll work with 2 or 3 feet, but I probably have a 20-foot long antenna in the basement because I am below ground, and that works just fine. This is the power from the wall wart, and this is the 1 to 5 volt output to the home automation system, so I can track it that way. These are some other variations that people have used for packaging, and you see some of them can be quite elaborate and they look quite professional. So this can go in any kind of a box. A lot of them are portable. As I said, mine sits on the bench, so it's fine where it is. Okay, so that's it. If you have any questions, please let me know, and please like and subscribe and click the bell so you'll be notified of any future videos I have. Thanks for watching.